So far, we've said a great deal about fatigue. And essentially, the Basque-Quinn equation sums it up all. The idea in the Basque-Quinn equation is that we are given the stress amplitude and we are trying to predict the fatigue life or number of cycles to failure. So that was cast in the context of this stress-based approach. The stress is given, and that's how we are trying to predict life. Presently, we're going to be concerned with an alternative scenario where we are given the alternating strain, let's say, and we are gonna again ask the same question. What is the number of cycles to failure? So we should compare a stress-based approach to presently an alternative way of posing the same question, but now therefore through this concept of strain versus stress. So this is going to be the strain-based approach to fatigue. And this is going to be meant eventually, or its strength, let's say, is going to lie in the low cycle fatigue region. So we are looking at strain-based approach for low cycle fatigue. Now we can immediately again remember that the transition between low to high cycle, so low to high transition, is not a very clear transition. It's sort of fuzzy, and it also depends on the material and on the application to a certain extent, but usually occurs around 10 to the 2 to 10 to the 4 cycles. So if we're just talking about less than 100 cycles, that's certainly low cycle fatigue. If we're talking about more than 100,000 cycles, let's say, that's certainly high cycle fatigue. But in between, it's hard to say whether it's low cycle or high cycle. But now we're going to pose a alternative way of framing the fatigue problem, the strain-based approach, which has eventually, compared to the stress-based approach that we've discussed so far, a series of advantages. And let us state here 4 advantages. The first approach, the first advantage is that it turns out it's a bit more general. It's going to be more general in the sense that eventually it has the potential to apply to the high cycle fatigue regime as well, although its strength is predominantly in the low cycle fatigue region. Moreover, it can make better predictions, again, especially in the low cycle fatigue region, where one can imagine that perhaps Basque-Quinn equation may still be employed, but the strain-based approach, it turns out, can do a better prediction in the low cycle regime. It was developed a little bit later, which is not an advantage on its own, but it was developed in the 50s, much later than the stress-based approach, which appeared somewhere towards the last quarter of the 19th century. But the fact that it was developed earlier was then one had the advantage of, let's say, keeping modern technological applications in mind in the construction of the model, and as such it is an advantage. That is something that makes it a bit more general and gives it a better predictive capability in such applications. And the advantage is one advantage is associated with low cycle fatigue, or this focus and advantage gives it the low cycle fatigue prediction advantage, and that focus is that it is something that works quite well in the case where you have significant plasticity, which is something that is not the strength, let's say, or focus, or an advantage, let's say, of the stress-based approach. In fact, the stress-based approach has disadvantages in terms of predictive capability in the presence of significant plasticity. So let us give a exposition of the strain-based approach. We're going to focus on the fundamentals, and the first thing that we want to acquaint ourselves with is the so-called cyclic stress strain curve. Now, the cyclic stress strain curve discussion that we are going to present here is somewhat brief, but it captures the essentials and gives us the essential background to proceed further into the discussion of the strain-based fatigue approach. Now, the idea is that we're going to eventually carry out strain experiments, fatigue experiments in terms of strain control. So we're going to prescribe not the amplitude, or in other words, the range of the stress. That's what we would do in the stress-based approach, but rather we're going to prescribe the range, or for that matter, the amplitude of the strain. So the range is twice the amplitude. So we are going to assume presently, remember when we started discussing the stress-based approach, the basic Baskin equation, one dimension, normal stresses, and no stress concentration, no mean stress. So presently we're going to assume that there is no mean strain, there is only one strain, and there is no notch, and that strain is the normal strain. So we're making, notice on the background, similar assumptions that are going to accompany our discussions. I'm not going to distinguish the alternating strain with an additional R that indicates that it's completely reversed. Presently, we understand it to be so. Now, however, one question one might fairly ask is, if the mean strain is equal to 0, does that mean that the mean stress is equal to 0? Now, that's what we are going to assume. Now, if we had a simple static loading, and if I give you what the strain is and it's 0, the stress is obviously equal to 0. But it turns out when you have cyclic loading, this map from 0 mean to 0 mean strain to 0 mean stress is not trivial. And I like to emphasize that. It turns out, and I refer to your books on a discussion on a more detailed discussion of this aspect. It turns out in cyclic loading with 0 mean strain you can have non-zero mean stress. But presently we're going to assume that, and it's not unrealistic in many scenarios, that 0 mean strain is accompanied by 0 mean stress. Let's keep that assumption in mind. So what we're going to do is we're going to do a stress strain experiment, a test, and in that test we are going to cycle the strain. So because we are controlling the strain, we're going to be prescribing its value, and let's say that value is going to be between a minimum and eventually a maximum. Okay, so that's the min and the max value. And subsequently, we're gonna load the structure. Now, suppose I did a uniaxial standard tension test. So what we would have in that scenario was, for instance, what we observed was, we would have, let's say, an elastic region, and then a sharp or a smooth transition into a region where we clearly see plasticity, and then the stress strain curve would proceed, and at some point it would probably go, and eventually, let's say, it would lead to failure. Alright, so that would be the case of a tension test, a uniaxial loading scenario where we monotonically increase the stress, or in this case, because we are controlling the strain, we monotonically increase the strain, and then we try to see what happens. Now, what we're going to do now is slightly different, because we're interested in cyclic behavior. So we're going to first load the material to a certain extent up to this point, but instead of continuing all the way to failure, at this point, we're going to unload, okay? And I'm going to do a cycle of loading that starts from this point. So we are already at some maximum strain, and we're gonna start unloading. And I know that unloading is elastic, and at some point, however, which actually might even occur before we hit zero stress, by the way, although we haven't discussed that in detail. But presently, let's proceed the way we have discussed. So we had assumed that unloading is elastic. We hit to that point. But what I'm going to do now is I'm going to continue further. Now, something strange happens when we continue further due to the nature of the material behavior. And we had yielded at this point, and the point of yielding continuously increasing. In other words, if I had unloaded and loaded back to that point, we would get yielding at this stage and continue along the same curve. But when we load in the reverse direction towards compressive stresses, it turns out yielding does not occur at the same magnitude, but it can occur a lot earlier. So this has to do with this hardening behavior that we discussed. If it hadn't hardened, it would go like this. But now it hardens, the strength of the material increases when we unload, but now what happens is strength under compression appears to diminish and yielding occurs earlier. And then the curve goes like this. And then we go to a certain value, to the maximum, to the minimum strain. And then when we hit that point, of course, we could have gone until something like failure perhaps happens, but we're going to stop and we are going to load back. And when we load now, when we remove, start to remove the load towards zero, again, it turns out that this behavior is elastic. In other words, I proceed on a line that is parallel almost to the initial line. So this is one line, this is another line, that's another line, and all of those lines are almost parallel to one another. So let me correct this a little bit. It's not exactly a nice parallel line, so let's do it like this. Okay. So all of those have slope almost Young's modulus. So we unload the structure towards zero stress, but then when we pull into the now tensile regime, stress is positive. Now again yielding, it turns out some sort of plastic behavior starts, which I distinguish by the fact that the stress strain curve starts to deviate from a line with slope Young's modulus again, and then this is how the curve goes. Okay, so let me just fix that a little bit here. Let's draw it like this. And I hit to that point. Okay, so we had the original uniaxial loading curve. We came up to a certain point, and then starting from that point, we're going to do now a full cycle where we start from this maximum strain, we unload, we continue, and then this compressive stress keeps increasing, and then we stop here, we start to remove the stress towards zero, we continue, and then we deviate from a line again, goes like this, and we come back to the same maximum strain that we started from. So you see we did one full cycle. Now, when I completed that cycle, notice that we did not end up on the same curve that we started from when we were starting the test, when we were approaching to the point of the start point of the one full cycle. So this one cycle, in fact, it is the first cycle. The way it ended up is significantly different than the starting stress strain behavior of the uniaxial tension test curve, uniaxial stress strain curve. And it turns out that if I were to do this once again, I would trace a line from max stress strain to minimum strain, a line for the stress that would again somehow differ from the first cycle. I do it for the third cycle, differs from the second cycle. The fourth cycle differs from the third cycle, etc. So every cycle will differ from the previous cycle by a certain amount. But it turns out that if we do this enough number of times, then that cycle starts to follow a closed path, which we are going to call the cyclic stress-strain curve or the staple hysteresis loop. So we're going to draw that next. But presently what we've observed is that even the first cycle differs significantly from the uniaxial tension test stress-strain curve, and every other cycle eventually will differ from the previous cycle stress-strain curve to some extent. Okay, so now here, first of all, notice that we are imposing strains that are so large that significant plasticity occurs. So for instance, in this very first unloading, this is the amount of plastic strain we have. It is significant plastic strain. In fact, remember that this slope is exaggerated. In fact, it's much more steeper, and therefore the initial elastic strain as well as this unloading line will be very steep. So at this strain, the amount of plastic strain is very large actually in reality for real Young's moduli compared to the elastic modulus, which appears large here. In reality, it's not so large. So this is a case where there are significant plastic strains. Okay, and moreover, if such significant plastic strains are observed, the behavior, stress versus strain, is significantly complicated. More complicated with respect to what? Well, if we were doing cyclic loading in the elastic regime, then the behavior is really trivial, because what I would draw in that scenario is simply a stress versus strain curve that it doesn't matter how we start the cycle. We can start from zero stress strain. I will increase up to a certain point. Let's say that point is well before yielding, and then I will unload, compress. It's well before revert yielding under compression, and then unload back again and cycle back and forth, always on a line. I'm on a line. There is no gap forming between loading and unloading curves, let's say. And so it's just a line and sort of trivial, right? That's what I mean by trivial. If plasticity involved, the behavior is a lot more complicated. Now, what we also see in the case of such cases is that when I go in one direction and follow back in the other direction, there's a significant gap at any given strain. Let's say that value of strain, the stress along one direction is compressive, the stress along the other direction of loading is at the same value of strain, is significantly positive. So the difference is just between the loading direction. Okay, so we call such a loop that displays hysteresis. So in this case, there is no hysteresis. We load back and forth along a line, but here we have an hysteresis. In other words, this area, this loop has some area inside that is associated ultimately with, as we've discussed earlier, with energy that is just, or work that is just gone where? Into significantly large plastic deformations. And now, if we are looking at such cyclic loading, and if I want to eventually discuss fatigue associated with such a loading, turns out that the stress-based approach may not be quite suitable, because essentially it turns out that let's say interpretation is that stress-based approach is for cases where there is little or no plasticity. Okay, and that interpretation is going to become a little bit more clear further on as we proceed through the strain-based approach. So now we've started discussing the cyclic stress-strain curve, and what I've said is that this first cycle differs from the initial uniaxial tensile loading significantly, and I said that every other cycle is going to differ from the earlier one to a certain extent, but if I do more and more cycles, eventually this cycle will approach a stable appearance, and that's what I would like to draw next.